Hello again. Welcome back. Last time we parted ways, we were on this screen. And so now we're going to do part two of chapter 5 in this presentation here. So again, I break them up so you don't have to sit there for too long at one time. You can plan your, if you want to do them back to back, that's fine. This way you can plan your time a little better, maybe. And maybe stay awake through one of these. That'd be nice. Anyhow, all right, we're now talk about risk management tool 11, preliminary hazard analysis. Now, when you hear me talk about PHA, it's usually in the context of process hazard analysis, which is mandatory in process safety management, which we're going to talk about later in this course. And so but the PHA now is preliminary hazard analysis, and it's an initial systematic analysis of a system design, facility, or process used to identify hazards and necessary control measures and allow for risk levels to be prioritized for further risk assessment and management. So you can see they're talking about here, you identify hazards, control measures, analyze them, prioritize them for assessment and management. This process is similar in a whole bunch of these things. So they just have little different takes on them. So its primary purpose is to identify and describe significant hazards that might arise from defects and unsafe conditions in the design and operation of a system or subsystem. It is especially useful in providing an analysis of current state risk levels and the risk reduction levels of proposed risk treatments. Preliminary hazard analysis, originally developed in the 1960s by the United States Army and published in the MIL Standard 882 standard, is a method to identify hazards, assess the initial risks, and identify potential mitigation measures early in the design stage. And as you know, in anything you do, the sooner you can catch something, the better off you're going to be. PHA is one of 8 risk assessment techniques listed in ANSI Z590.3 that the standard states are sufficient to address most risk situations. PHAs are now used by many industries to examine existing systems, prioritize risk levels, and select those systems requiring further study. Application. PHA is often used as an exploratory analysis early in the conceptual development stages when little information is available on design details or operating procedures. Sometimes used as part of a design safety review process, PHAs help identify potential hazards. The results of PHAs often lead to more detailed risk analyses. The process steps for a PHA are similar to other hazard and risk analyses. No surprise there, right? The PHA procedure is described in the following steps: establish context, establish a team, develop a list of hazards, select development of PHA worksheet, estimate current state severity, estimate current state likelihood level, estimate current state risk level. Where do you find severity, likelihood, and risk in? A risk matrix, right? Select proposed risk control, estimate future state severity, likelihood, and risk levels. So you can see that, and this is done in same things are done in a lot of different ones of these too. So, so here's the kind of a biodiesel production, methanol vapor release. I'm gonna have to put my specs on here to see this one. So here's their hazard ID number 3. All right, you know, start number 3, whatever. Hazard description: human factor error, explosion resulting from overfill, spill, methanol tank, and ignition source. Exposure description: operator fills tank from tanker truck using float gauge to determine fill level. Requires visual attention on the gauge. Manual shutoff, tanker truck running during filling. Exposed assets: employees, third-party delivery personnel, process, facility, local community. Existing controls, SOP, which is standard operating procedures. Severity levels 5. That's pretty high. So, and likelihood is 3. So that's a risk, what an RL risk level, I guess, is 15. Proposed controls: engineering, overfill protection design, auto alcohol resistant fire extinguisher system, auto overfill shutoff, spill containment. Warning. Remember, some of these people call warning as one of the hazards in the hazards of control, but we would call it an administrative control. But anyhow, fill alarm, mechanical integrity program. The mechanical integrity program is part of process safety management as well. SOPs, so are SOPs, and so is training. So there's no PPE listed here. That makes sense but then they took the severity, which is still a 5, down to a likelihood of only 1, and the risk level then back went from 15 to 5. So you can see how they did the existing controls and proposed controls, and you'll see that same kind of thing in a couple of different things. And the other 2, you can read them, and come pretty much the same idea behind them. I'm not going to read the other 2. They're in the book, and you can read them, but you get the idea. Then they've come now. But notice that under proposed controls, the existing controls aren't very much. So they put engineering controls, administrative controls, and there's no PPE because it's the nature of the beast. But you can see that that's not these aren't new concepts here at all to anybody here in this course. Excuse me. Now, 12 is a what if analysis. Now, when we get into process safety management, you'll see that last one we looked at was awful similar. Right? A what if analysis. What if hazard analysis is a team-based qualitative method used for identifying and analyzing hazards, hazard scenarios, existing controls, and needed additional controls. Again, here we go. Existing controls and needed additional controls. You can see a pattern here. It was developed in the 60s by the British chemical industry as an easier, less costly method similar to the hazard and operation study known as HAZOP. The primary objectives of What If are to identify and analyze the system's major hazards and hazard exposure scenarios, causes, deviations, or weaknesses that can lead to hazards, existing controls, and needed controls to achieve an acceptable risk level. Although originally developed for chemical and petrochemical process hazard studies, so see they touch on it here. There's a lot of time they say something like this, but they don't want to acknowledge that process hazard, process safety management exists. They allude to it because that's what they're probably talking about here. Because chemical and petrochemical processes almost always come under process safety management. So again, although originally developed for chemical and petrochemical process hazard studies, What If and its variations have become widely used in many other industries, including energy, manufacturing, high-tech, food processing, transportation, and healthcare, to mention a few. The method can be applied to a system, process, or operation at a more specific focus, such as a piece of equipment, procedure, or activity. And What If is really what they do. It's called a What If checklist in process safety management. So that's what they're doing. What if this happens? Okay. So the What If hazard analysis is a team-based brainstorming process used to identify and analyzing hazards of a system or process. And I guess it's kind of like brainstorming. Cross-functional teams knowledgeable in the process discuss aspects in a random, creative fashion, asking what-if questions to identify any weaknesses, deviations, or hazard. The team identifies potential hazard scenarios, their causes, any existing controls for these hazards, and additional controls needed. A spreadsheet is generated listing the tasks or elements and posed what-if questions, along with the resulting consequences, existing safeguards, and recommended additional controls. For this method to be successful, a skilled and knowledgeable leader able to facilitate the analysis and keep it on track is required. A recorder or scribe is needed to collect and document the findings. So what happened in this thing in process safety management? We all got together, would have a cross-section of people. Obviously, the people worked on the ammonia system, and myself and the safety department would be there, and usually our engineer, and we would have we already had a predetermined number for this particular piece of equipment. Okay, what if this failed? What if this happened? What if this happened? And we'd go through each one of those and look at them and make sure they were okay. Now somebody could come up with some new ones too, but also somebody came up with some crazy ones. Like one of them was like, what if an airplane hit the plant? Well, we weren't in a flight path for any airports or anything like that. So the possibility of an airplane hitting our plant is pretty slim. Do we really want to spend time on something like that? So we took that out because we didn't think that was feasible. Now, it might have been they were doing a facility that was under the flight path of an airport. In that case, maybe that needs to be in there. But if an airplane hits your plant, probably not much you can do about it. So this is the what if analysis. And again, here comes specs again. What if the relief vent fails during thermal expansion of methanol vapors? Causes could be corrosion of the vent or damaged vent. The relief vent, they call it. Okay. Overpressurization, rupture, fire, explosion, control of the consequences. The controls are PM schedule and inspections. So PM is preventive maintenance schedule inspections. Not recommending controls, non-corrosive vent valve, temperature pressure alarm. So the vent fails. If corrosion was the cause of the vent, then why wouldn't you have a non-corrosive vent valve? They're talking about a valve here, I think. They say a vent valve. It's like a pressure relief valve. So then, or an alarm, it could be on there too. So again, you can read in the same thing. There's causes here, like 3, during the filling of methanol tank, the tank is overfilled, distraction, miscalculation. Consequences, explosion, local population exposure. Controls are in place, or SOP and training. And this is kind of like similar to the one we talked about before. Recommended controls: auto fill design, auto shut off, overfill alarms, auto fire suppression. So you'd see it kind of like the same method. I mean, same problem there. And they just now handle it through a what if analysis. Not much different though. 13, failure mode and effects analysis. This is an interesting one. Now, failure mode and effects analysis is a more detailed qualitative or semi-quantitative method used to identify and analyze the ways in which system components can fail and the resulting effects to the system. FMEA uses a spreadsheet with columns. Hey, there you go, a novel idea. To analyze individual process functions, potential failures, causes, effects of failure, and controls. Developed in 1949 by the U.S. Department of Defense and published in the Mills Standard MP 1629. That won't be on a test. Procedures for performing a failure mode effect and critical analysis. FMEA's objective was to classify possible failures related to personnel and equipment. Remember, you have to look at just people as well. Lately, it was used by NASA and the nuclear industry. Currently, it is one of the most widely used methods by a number of industries. FMEAs are performed to analyze system components individually to identify potential failure modes, their causes, existing controls, and resulting effects of a failure on the system. Traditionally used as a form of reliability analysis of systems, subsystems, processes, and hardware, FMEA are now used to analyze jobs and tasks, identifying potential deviations from desired performance criteria that can cause failures or exposure to hazards, and how these can occur, as well as resulting effect on workers and environment. FMEA is designed to identify and analyze failures and the resulting risk exposures by making the risk descriptors and selected risk scoring system important to the analysis. Many risk scoring models use two-factor systems based on severity and likelihood shown as severity times likelihood equal risk level. That's the most common one, and that's on that basic 5x5 that we use. And I personally like that. You could do severity plus likelihood. Remember now, way back in the beginning of this whole process, we call establishing the context. This is one of the things you would establish. What are you going to use? What type of tool here are you going to use? Type of risk matrix you're going to use. More complex risk scoring systems used by methods such as FMEA include a third and sometimes a fourth variable. FMEA methods typically use severity, likelihood, detection of failure in their risk scoring systems. This is interesting. This is another thing thrown in here. The detection rating is based on how easily the potential failure can be detected prior to occurrence. I'm not sure what they mean by prior to occurrence, because how could you detect something that hasn't happened? But I think what they mean, how can it be detected as soon as it happens? In other applications where hazard control measures are analyzed, a prevention effectiveness factor is used in place of detection. Prevention effectiveness is an estimate of a control measure's effectiveness and reliability in controlling the failure and its effects. This estimation is based on the hierarchy of controls model and may be preferred by OSH Professional since it aligns with ANSI 590.3, prevention through design concept. The following risk scoring formula is used in this example. So severity times likelihood divided by prevention effectiveness equal the risk level. So there you go. That's another way to determine it. You're still taking the severity times likelihood, then you're dividing it by the prevention effectiveness. So I don't think they give us an example for that in here. Failure mode and effects analysis takes the system and breaks it down into individual components or modes, or nodes they're calling it here. Each component is systematically analyzed for the different ways it can potentially fail and the effects of each failure on the system. The process steps are presented in the following slides. Establish the context. There you go. The purpose and scope, the systems to be analyzed, time frame, limitation, resources, and definitions to be used. In this example, severity will be multiplied by likelihood, and then this product divided by prevention effectiveness to get the risk priority number. The risk priority number, of course, is the N number, which we're going to use to determine which ones get looked at first. Select an FMEA team, an experienced facilitator, and a qualified cross-functional team from safety, engineering, production, quality assurance, human resources, operators, outside experts or consultants, and others are, as appropriate, are selected. This team can be pretty good size sometimes. Gather data on the systems, operations, procedures, diagrams, loss history, and other available information, including any previously performed hazard analysis. And get all your stuff together. Identify process functions. The primary functions or process steps are identified for analysis. Each is entered into the first column of the spreadsheet. Identify failure modes for each function. There may be multiple failure modes for a function, but there probably are. These are listed in the second column. Identify effects for each potential failure mode and put them in column 3. This step is critical and must be studied carefully by the team. So in other words, if this valve fails, what's going to happen? That's critical. The effects of it, the consequences. Again, they use different words for the same thing a lot of times. Determine severity for each effect. An example of severity level is insignificant, 1, negligible, 2, 3, marginal, 4, critical, and 5, catastrophic. That's just an example of one somebody's in somebody's mind at a severity level. Identify potential failure causes, enter in column 5. This requires a close review of past experiences and previous loss analysis, observations, and experiences. Determine likelihood for each cause and record in column 6. And there you go. Unlikely, seldom, occasional, likely, and frequent. So you got a 5x5 matrix here. Identify existing controls, if any. Record them in column 7. Now, if you're looking at an ongoing process, there's probably some controls in place. Determining prevention effectiveness. Using the hierarchy of controls, the team evaluates the effectiveness and reliability of existing control measures. Assign a prevention effectiveness rating and enter in column 8. And this will be the effective, avoid or eliminate, substitute, or multiple engineering controls. In other words, if it avoids them and eliminates them, then it's going to be a 5. If you can substitute something or multiple engineering controls, it's a 4. A single engineering control is a 3. Warnings or administrative control is a 2. PPE or none is a 1. Combine severity and likelihood ratings. Multiply the severity from column 4 by the likelihood from column 6 to provide a risk rating, which is entered in column 9 and again in column 14. Calculate initial risk. Divide the number in column by the prevention effectiveness from column 8 to get the initial risk priority number, which is entered in column 10. Next is what the worksheet looks after this step. Okay, this is the FMEA worksheet, first columns. Process function is handling a lashing rod overhead. This is going to be for what they're going to do here. They're lashing ship containers. Okay. Potential failure mode, fall from elevation. Potential effect, death. Yeah, if you're up in a high, you fall, you're going to die. It's 5 severity, because death. And potential cause of failure, unsafe practices. The likelihood is a 3. Current controls, there's none. So the PE is 1 because there's none there. And S times L is 15, so the RPN is 15. Additional controls. For initial risk priority levels that are considered above the acceptable risk level, additional risk reduction controls are selected using the hierarchy of controls. Enter such controls in column 11 for each control. Identify the responsible party and target date for implementation and record in column 12. Now, this comes about, and some of these mention this, but this is a good idea. If you get together as a group, you say, okay, we're going to do this. We decided that we need to do this, put this control into this. All right, somebody has to be the PP, primary person responsible for that. You just can't say, we're going to do this, and then we'll come back next week. Do we do this? Well, no, that's what happens. Somebody needs to be responsible, and you put some kind of a date. Sometimes the date might be 6 months down the road. It might not be easy. Sometimes it could be tomorrow. So you got to put some kind of a date and somebody who's responsible for it. Verify the actions taken. Following implementation of added controls, a review is performed to verify that the controls are effective and no additional or unintended consequences are created. Enter in column 13. So again, you have to verify the controls are effective. What good are they if they're not effective? Of course. Reassess prevention effectiveness and additional controls and record in column 15. Calculate the revised risk priority number by dividing the number in column 14 by the number in column 15 and write this in column 16. This is the revised risk priority number. So this is what the the whole thing looks like. We did up to 10 on this one. So let's look at number column 11, the needed action railing system, SOPs, PPE, fall from elevation, responsible party and target date management. Now that's lame, but actions taken to reduce likelihood of falls. The S times L here is still 15, but now the prevention effectiveness now is 4 instead of 1. So now your RPN2 is 3.75. It's 15 divided by 4. Here was first line in column 8, 9, 10. It was the 15 divided by 1. And now we have the 15 divided by 4. And they changed the columns, which for some strange reason. So you can see what they've did on the next one, repetitive motion while handling a lashing rod overhead. This is a repetitive motion injury. And risk prevention number was 4. 3 times 4 is 12. Well, they got these columns wacky a little bit. And then they took the 12 over there, divided by the prevent PE of the prevention effectiveness of 3 and got a 4. So they took this RPN that didn't change. RPN here, they took it from 10 down to 3.33 by changing the prevention effectiveness number. That's all they did on that one. So you could see they're similar. The prevention effectiveness, that's an awful big number to take it down. I don't know if you couldn't just handle that instead of the prevention effectiveness and handle that in the likelihood and just change the likelihood. But this is what they're doing in this particular example. That's fine. They can do whatever they want. You can use this if you want to too, but I wouldn't. I'd have my columns here to be the same, not this. They're cockeyed here. Confusing a little bit. 14, layers of protection analysis. Layers of protection analysis is a barrier analysis method used to study existing or proposed barriers for a hazard scenario or situation. Its purpose is to determine if current barriers are sufficient to achieve an acceptable risk level, and if not, what additional barriers are required. Application LOPA is used qualitatively to review layers of protection between a hazard and a consequence, or semi-quantitatively to prioritize processes for further analysis. LOPA can also be used quantitatively to analyze each independent protection layer, IPL, independent protection layer, and safety integrity levels, SIL levels, for risk reduction provided. As described in ISO 31010, hazards and consequences are selected and independent protection layers are identified for each hazard consequence pair. IPLs are defined as physical barriers or devices that prevent the initiating cause of a hazardous event from proceeding to the unwanted consequences. IPL controls include physical barriers, which are called engineering controls, and controls such as design changes, engineering controls, warnings, and alarms, which are administrative controls. So this is the layer of protection analysis. And this is, let's look at the thermal expansion vapor generation, the first event. This is a little bit better done spreadsheet. Cause, sun/vent failure. Well, we can't do much about the sun, huh? Independent protection layers are the tank vents. Current state of existing IPLs is severity 5, likelihood 3, risk level 15. Propose additional independent protection layers. Now, independent protection layers, this is really like a control. Like I said, then they use different numbers. Shade protection for tanks, explosion-proof equipment, internal pressure alarm, spill containment, automatic fire extinguishing systems. And now the severity is still 5, but now with all those 1, 2, 3, 4, 5 things in place, the likelihood is 1. So the risk level went from 15 to 5, and that's achievable. I mean, that's nice to know. It's a good outcome. The second one, corrosion, methanol tanks, trim and piping. Independent protection layer 1 was a nitrogen blanket, and now they're going to propose corrosion inhibiting materials, cathodic protection, auto fire extinguisher system, spill containment, and saving. Again, the severity doesn't change, but the likelihood does. You're not changing the severity on these things, you're just changing the likelihood. And they got that risk level down to a 4. And the third one, the human factors, methanol tanks overfilling. Now, I don't know why you think they would have had this overfill tank design, automatic shut off, and all that stuff in there before, but obviously they didn't. So that was a pretty high risk level, but they got it down to a 4. So you can see that how this is done is a pretty good example. Layers of protection. And what they're doing here, that's what they're doing on 3, 4, 5, 6, and 7. Those are independent layers of protection. So they're different types of controls. Shade protection, because the sun heats up the tanks. So keep it out of the sun. Explosion-proof equipment, internal pressure alarms. There's different independent protection layers or different controls. Bow tie analysis. The bow tie method provides a big picture view of a hazard scenario and its relationship between hazards and causes, barriers to prevent occurrence, and mitigating controls to reduce the impact should an event occur. Bow tie analysis is a relatively new method that combines a simplified fault tree analysis, left side of the bow tie scenario, and simplified event tree analysis, right side, used to provide a clear illustration of the risk pathways and control measures in place for a hazardous event. I don't think it's all that clear. Yeah. Its purpose, we'll look at it though. Its purpose is to analyze the adequacy of barriers to prevent the occurrence, as well as a barrier to mitigate the impact in the event of occurrence, so that the risk can be visualized and communicated to decision makers. Now, that's a good idea. It's something to prevent the occurrence, but it also has something in there that might mitigate the impact if you do have an occurrence, such as spill containment. You didn't stop it from happening, but you're going to contain it. Oops. Bow tie analysis provides a view of existing barriers to prevent the occurrence of hazardous events and existing reactive measures to reduce the severity of the consequences should the event occur. Did we skip one here? There we go. All right. In addition to analyzing barriers, bow tie considers existing or potential escalating factors that have the ability to reduce the control's effectiveness or reliability. Escalating factors are elements or conditions that can lead to failure, bypass, or minimization of barrier controls. The table below several examples of escalation factors for preventive measures and mitigative measures. So preventive measures, preventive maintenance, escalating factor, backlog of maintenance, preventive maintenance delay, escalation controls, internal audit. Preventive measure is pre-shift cleaning, escalation factor, low concentration of cleaning agent, escalation control, conductivity measurement of cleaning liquid. So, okay. Mitigation measure, product recall. Escalation factor, incomplete traceability data. Escalation control, periodic traceability test. Mitigative measure, emergency action plan. Escalation factor, key personnel unavailable in an emergency. Escalation control, adequate number of alternate personnel for emergency action. All right, well, that makes sense. Bow tie analysis provides a view of existing barriers to prevent the occurrence of a hazardous event and existing reactive measures to reduce the severity of the consequences should the event occur. So that's what we're talking about here. That's why they call it a bow tie analysis. You can see right now from this thing here. So hazards, causes, prevention controls, escalation factors, and then and in the middle of the scenario, then the mitigation controls, resulting consequences for other mitigating controls. Now, striped bow tie assessment is the purpose and application of a modified striped bow tie risk assessment are basically the same as for a conventional bow tie. However, it is designed to provide more detailed risk-based information. The conventional bow tie method has several weaknesses, including its lack of a risk scoring mechanism and its lack of a differentiating controls and their effectiveness. The striped bow tie was developed by the authors to help provide more risk-based information by incorporating a risk scoring system, the hierarchy of controls concept, and a simplified layers of protection analysis. The process steps are similar to bow tie with several additional steps. See example next slide. So you can see, here you go. That's why they call it striped bow tie. The layers of protection. Now, this is kind of slick on the left-hand side. The layers of protection, there's rainbows colors there. Elimination, substitution, engineering, multiple engineering, single, warning, administrative, and if not PPE, but because in these, I guess in these processes that wouldn't be appropriate. So they're down there and they're throwing. They don't tell you what they are, but they're an engineering control, which is going to give you a 0.6, warning 0.8. And total RR. Risk reduction 6.48. I don't know where they got it from. And hazard 3, hazard 2, hazard 1. but you can get the idea here. The methanol vapor release, then it happens. The scenario doesn't happen. So now the layers of mitigation, engineering, administrative, financial layers of mitigation. So those I've never used them or I've ever seen them used, but that's the last of these things. But you can see through a lot of these things, you're really taking, if you just take your basic risk matrix, that's kind of like almost a given in most of these things. And you can modify that somewhat if you want to. And the processes aren't that different. And also in this particular, this the what if analysis, the FMEA, they're really, really similar. And so, but anyhow, these are all interesting. There's all your stuff on that. So that's it for chapter 5 video. Read the chapter. It's pretty interesting. And do all the other stuff that's required here, and you'll do fine. And in the meantime, be safe.